Alright, dear children, we will again continue with this concept of alpha particle scattering experiment that you are learning the last YouTube video. Okay, now we discuss up to 3 important observations which was made by Rutherford. But one question basically arise out here, and this will may ask in the examination also, is that for alpha particle scattering experiment, why we are choosing gold as a metal, okay, for the scattering of alpha particle? Why not with other metals? Okay, now the reason is that, and why the gold must be a thin, and it must be in the what? Foil. The foil means a very thin sheet, a very thin sheet. Okay, so the gold, a thin gold foil was taken in this experiment called, as I said, called what experiment? Alpha particle scattering experiment, due to number of reasons. And children, this topic is important for examination. Some reasoning question may ask, okay, why not with other metal? Now there are a number of points that can be added that we can understand, okay, so that the gold foil was taken in alpha particle scattering experiment. So one of the point is a very thin gold foil was taken to ensure that alpha particle was deflected by a single collision. That means the foil must be taken very thin so that the atom constituting the foil must be in that foil must be a single atom in that foil. Okay, so that whenever alpha particles goes and strike to the atom, okay, that scattering or deflection of this alpha particle takes place only with a single collision, not with a multiple collision. So with single collision, you can clearly see that by what angle the alpha particle gets scattered in different direction. So due to this reason, the very thin gold foil was taken. Okay. Now another reason why gold foil is only taken, because the gold foil was taken because gold can be beaten into a very thin foil. Yes, gold is one of the metal, and one property of metal is metal has a malleability property. That means it can be drawn into a very thin sheet. So that's why gold foil was taken, because gold can be beaten into a very thin foil. Okay, for this reason the gold foil was taken. Next, the last point is gold is one of the metal, and the nucleus of gold foil is usually heavy. It's a heavy nucleus. Okay, so that's why the gold nucleus is heavy, and this heavy nucleus basically produces a large deflection in what particle? Alpha particle. So in order to know the scattering of alpha particle by a large range of angle and to produce large deflection, okay, the gold or heavy nucleus must be taken, and gold is one of the heavy nucleus which was taken. Okay, so these are the point which is basically asked in this particular experiment. Okay, now there are 2 more observations that I want to add regarding this experiment observed by Rutherford, and the conclusion which was made by Rutherford. The fourth experimental observation and the explanation which was even made by Rutherford is actually the scope of Coulomb's law. You know, Coulomb's law means the law which measures the force of attraction or repulsion between the 2 charges. They usually call as what charges? Point charges. Okay, that means the charges can have attraction or charges can have what? Repulsion. Okay, but from this experiment we understand that Coulomb's law is also hold for atomic distance also. Atomic distance what? Also. So for that, Rutherford has assumed that when alpha particles were made to pass through the what? Atom of gold foil, we definitely see that there is a what force exert between the alpha particle and the atom of the gold foil. That is a what force? Repulsive force. Now the reason as the repulsive force exert is due to the repulsive force exerted by the nucleus, because the first thought observation said that every atom consists of a very small space, okay, in which the whole of the positive charge is concentrated, and that space is called nucleus. So this is the atom and this is the nucleus where the positive charge is present, and alpha particle are also positive charge, and between positive what happen? Repulsion takes place. Okay, so force of repulsion exerted by the nucleus on this alpha particle, okay, alpha particle is in accordance with the Coulomb's law. That is, this force is inversely proportional to the square of the distance of the particle from the nucleus. That means you can see in the diagram, when the particles are very close to the nucleus, this nucleus exerts a strong repulsive force, and due to that the particles get deflected by an angle greater than 90 degree. But when the alpha particle and the distance of the nucleus are large, that means when the distance increases, the force, repulsive force exerted by the nucleus to the alpha particle decreases. That's why that alpha particle get scattered by less angle. Okay, so this scattering or deflection of this alpha particle by the nucleus is actually in accordance with which law? Coulomb's law. So as for the diagram, you can see the particles on passing through the atom remain quite far from the nucleus, experience a very small a repulsive force, whereas the same particle passing through the nucleus of an atom, very close to the nucleus of an atom, experience a strong repulsive force. Okay, due to that particle scattered or deflected by large angle. So Rutherford, on the basis of this Coulomb's law, on the basis of Coulomb's law, okay, calculated the number of alpha particles scattered at different angles and found that scattering of alpha particles by the nucleus is in accordance with which law also? Coulomb's law. So Coulomb's law is basically measure the force of attraction and repulsion between the charge only. But from this experiment, we understood that the Coulomb's law equally hold good for atomic distance also. Okay, atomic distance also. So this is the fourth experimental explanation and the observation made by Rutherford. Now we have a last one. So we deal with the last experimental observation and explanation made by Rutherford. Now in the fifth and the last experimental observation made by Ernest Rutherford, Rutherford actually acquired the knowledge of positive charge, in the nuclei of the atoms of different metals. Means he performed the experiment not only with the atom of gold foil, he performed the experiment with the other atom of metals, okay, which can be drawn into thin sheet. So by performing the experiment, okay, like he made alpha particle to fall on the foil of different metals, like gold was taken at that time, silver, he performed with the silver, platinum, these are also the metals which can be drawn into sheets, and counted the number of particles scattered in a different direction with the help of that counter called scintillation counter, and found that this number was not found to be same for all the metals. So from this he made the conclusion that the magnitude of positive charge in the nuclei of different metals is different. That means the amount of positive charge present in the nuclei of different metal are not same, are different. Yes, this is true. Okay. Now it was even found that greater the positive charge in the nucleus, greater will be the repulsive force exerted on the particle? Alpha particle. Means more the number of positive charge particle, okay, in the nucleus, more is the greater the force exerted by repulsive force exerted by the particle on exerted by the nucleus on the positive charge particle. Yes, this is true, because we know according to Coulomb's law, F equals to Q1 into Q2. When the charges, magnitude of product of charges increases, force also increases. Means more the amount of charge present in the nucleus, more the force exerted. And what force? Between the like charges, repulsive force. Okay. So the fourth final observation that, as I said, mentioned by explained by the Rutherford is the magnitude of positive charge in the nuclei of different metals is different. It's not same. But one of the great scientists called James Chadwick in the year, okay, let me just write down, in the year 1920, one of the scientists called James Chadwick. So one of the scientists, okay, who actually determine the positive charge in the nuclei of different metals, and found that the positive charge in the nuclei of different metal is equals to ZE. So I am writing this way, ZE. And you know very well, children, that this Z is actually a constant for a metal, for a given metal, and this Z is actually called as what number? Atomic number. This is called what number? Atomic number. So nucleus is always a positive charge, but the positive charge of the nucleus is always measured by plus ZE, where E is the charge of what? Charge of the electron. And Z is basically a constant for a metal, but this is different for different metals, and this Z is usually called what? Atomic number. Okay, and you know actually that atomic number is the number of protons present in the nucleus of an what? Atom. But in the year 1920, as I said, the positive charge of every nucleus of an atom is measured by plus Ze. But this positive charge of the nucleus of different metals are different, and that can be calculated by plus Ze. So this is also one of the important and the final experimental observation which was made by Ernest Rutherford. Okay, so we have done in detail about the alpha particle scattering experiment, experimental observation, and the conclusion drawn by what? Rutherford, the discovery of nucleus. Okay, now in the next YouTube video, you learn about the Rutherford model of atoms. Okay.